Example 1 says, in a small country, the current population is 200,000 people, and it is increasing at a rate of 2% each year. Most of the people eat rice as a basic part of their diet, and the country can produce enough rice for 300,000 people. Assuming they continue to produce the same amount of rice each year, how long will it be before there are shortages in rice and they have to start importing it? So what we want to do is we want to create an exponential model. So I'm going to, let's call it P of t to represent the population after t number of years. So this is equal to our starting value, which is 200,000. And I know that the population is increasing by 2% each year. That means that our common ratio, or our growth factor, is going to be 1.02. Now, sometimes students are inclined to make the growth ratio 0.02, but remember, if our growth factor is between 0 and 1, that means that we have exponential decay and our output values would be decreasing. That's why it needs to be 1.02. And then our exponent is going to be t. Now, we are trying to figure out the amount of time it takes before our population reaches 300,000. And remember, P of t represents the population. So what if we replace P of t with 300,000? And our goal is to solve for t. Up until this point, we haven't had much success solving for any kind of variable that's been in the exponent without using either the method of guess and check or some kind of graphing utility to see where the two curves intersect. So I'm going to start off by dividing both sides of this equation by 200,000. And dividing by powers of 10 is nice because these zeros are just going to disappear and these will divide out. So at this point, our new equation becomes 1.02 to the power of t is equal to 3/2, or 1.5. So our goal is to try to figure out what t is, and again, we don't really have the ability to do that yet unless we use the method of guessing and checking values of t, or using some kind of graphing utility and graphing this curve and seeing where they intersect. But in this section, we'll learn about a new type of function that will allow us to figure out what t is. So let's introduce that new function. If b is any number such that b is positive and not equal to 1, then the logarithmic function with base b is the function f of x equals log, so that spells out log and it's short for the word logarithm. And then we have base in the subscript, so we say log base b of x. So this thing here, the way that we read that, we say log base b of x. That is how we would read that function there, which is defined as, so the way that we define a logarithm is such that y equals log base b of x is true if and only if, this is what that double-sided arrow means. It means if and only if b to the power of y is equal to x. So now we have a way to go from, this is called an exponential statement, to a logarithmic statement, and we have a logarithmic statement go to an exponential statement. So we can kind of switch between these two forms, and that's what we're going to see in example 2 and 3. Example 2 says, write the following in terms of logarithms. So here we are given an exponential equation or an exponential statement, and we want to convert it into a logarithm. So we're starting with this form here, and we want to end up in this form. So how do we do that? Well, this here we can see from this generic formula, this is b, this is y, and then this thing here, this fraction represents x. So we would say, rewriting it here, we would say -3 is equal to log base 11 of 1 over 1,331. So this is the answer for part A. We've taken our exponential statement and rewritten it as a logarithmic statement. In part B, we have 4 to the 7th power is equal to 16,384. So here, 4 represents our base B, 7 we can think of as y in the above form, and then 16,384 would be x. So we can write 7 equals log base 4 of 16,384. And it doesn't, the equal sign, or I mean, this is an equation, and so this would be the same thing as writing it is equal to 7 this way. So either way works. So I'm just going to write it like this. In part C, we have 2 over 7 raised to the negative third power is equal to 343 over 8. So again, we want to write this in the logarithmic form. This thing here represents our base B. So I'm going to write log base 2/7 of, here is our x value, 343 over 8 is equal to, and then this exponent represents our y value, -3. So this is how we would write that in logarithmic form. Example 3 says write the following in terms of exponentials. So now we're given the logarithmic form and we want to write it in the exponential form. So we're starting with this form here and we want to end up in exponential form here. So the log base represents the base here. So we have 1/6 raised to the -2 power is equal to 36. And you want to note and make sure that this is a true statement, and it is. If I raise 1/6 to the -2nd power, then that would give us 36. So here is our exponential form. In part B, we'd have 12 to the 4th power is equal to 20,736. So this is what we are looking for. And then in part C, we have 9 to the 5/2 power is equal to 243. And if you need a quick reminder, the way that we deal with fractional exponents, that is the same thing as if I raise something to the 5/2 power, I could think of it as 9 to the 1/2 power raised to the 5th power, and I would need to multiply the exponents that would give me 5/2. But if I raise something to the 1/2 power, that's the same thing as the square root. And the square root of 9 is 3, so it also happens that 3 to the 5th power is equal to 243. So that's how you deal with rational or fractional exponents. Example 4 says evaluate each of the following logarithms without a calculator. So part A, we have log base 4 of 16. I don't know what this number is, but one thing that might help us is I could rewrite this in the exponential form. So if I rewrote part A in exponential form, that would tell us 4 to some power is equal to 16. And the value of the exponent or the question mark that makes that true is 2. So log base 4 of 16 is equal to 2. Let's try the next one, part B. We have log base 2 of 16 is equal to some value. Then I would have 2 to some exponent is equal to 16. The value that makes that true is 4. So I'd have 2 to the 4th power is equal to 16. In part C, we have log base 6 of 216. So that would tell us that I have 6 to some power. And if you want, you could also put to the x power instead of putting a question mark. And so what power of 6 gives us 216? That is going to be 3. All right, part D, we have log base 5 of 1 over 125. I know that 5 cubed is equal to 125, but that's not quite what we want. We want 1 over 125, but we know that that's also the reciprocal, so 5 to the -3rd power is the same thing as 1 over 5 cubed, and we just said that 5 cubed was the same thing as 125. So I could write 5 to the -1/3 power, or excuse me, 5 to the -3rd power is equal to 1 over 125. So here this is equal to -3. In part E, we have log base 1/3 of 81. So we want to ask ourselves, if I raise 1/3 to what power is equal to 81? And because 1/3 is a fraction, we're going to need our exponent to be a negative number. Because if I raised it, say, to the second power, that would be 1/9. If I raised it to the third power, that'd be 1/27th. And so those values would be getting smaller. So I know that 3 to the fourth power is equal to 81, so then this would be -4. All right, last one, I want to say 3/2 to what power gives us 27/8. How am I getting this? Well, the way that exponents work, I can distribute that exponent to each the numerator and the denominator. So that's another way of saying 3 to what power over 2 to what power gives us 27/8. I know that 3 cubed gives me 27 and 2 cubed gives me 8. So the value here is 3. So let's go over two very special types of logarithms. The first one is called the common logarithm. So the logarithm with base 10 is called the common logarithm, and it is denoted by omitting the base. So in other words, log of x is equal to log base 10 of x. Because our number system is base 10, that's why we call this the common logarithm, and we use it so frequently that we omit the base. So writing log base 10 of x, that's not something that we do. We just omit the base and we call it log of x, and this is something that we use very commonly. The other common, or the other frequently used logarithm is the natural logarithm. So the natural logarithm has a base e, and it is denoted by ln of x. So this is not a notation that we use, but that is what this means. We write ln of x, and ln stands for natural log. And the reason that the letters are switched, because sometimes students will ask me, why isn't it not nl? And it's because it's derived from the Latin word, or the Latin words for natural logarithm. Okay, so below in this purple box, we have some properties of logarithms. If we are taking the logarithm of 1, that is equal to 0. If we're taking log base b of b, that's going to equal 1. If I have log base b of b to the x power, that's equal to x. If I have b to the power of log base b of x, that's equal to x. And then the remaining properties are the analogous properties, now just using the natural logarithm. So make sure that you have those properties memorized. They're important, and they'll appear many times in future mathematics. Example 5 says, evaluate each of the following expressions involving logarithms. You may need a calculator for some of them. If so, round to 3 decimal places. So log of 100, this is the common logarithm, so our base is 10. So we're asking what power of 10 gives us 100, and the value that makes this true is 2. In part B, we have the natural log of e to the 9th power, and if you notice, that corresponds to property 7 here. So because we have the natural log of e to some power, this is equal to just whatever the exponent is, or the power. So this is going to equal 9. For part C, we have log of 1 over 1,000. And to help me out, I'm going to rewrite 1 over 1,000. I know that that's the same thing as 1 over 10 to the third power. And 1 over 10 to the third power, I can actually rewrite that as 10 to the negative third power. And so now we can look back up at the properties, and this corresponds with property 3, because even though I'm not putting the base here, it's 10. So because the bases match up, then the final answer would just be whatever our exponent is. So this is going to equal -3. And that should make sense because 10 to the negative third power is equal to the inside of our logarithm, which is 1 over 1,000. Okay, so part D, we have the natural log of 5. So this is essentially asking us what power of e gives us 5. And unfortunately, this is not an integer answer because e is an irrational number. So this one we would need to use a calculator for. I know that e to the first power is about 2.718, and I know that e to the second power is approximately 7.389. So our answer, whatever we get, is going to be something between 2.718 and 7.389. So this you can just throw into your calculator, and if you do that, you end up getting this is approximately 1.609. Same thing with log of 14. I know that log of 10 is equal to 1, and I know that log of 100 is equal to 2. So log of 14 is somewhere between 1 and 2, and it's approximately 1.146 if we're rounding to 3 decimal places. Lastly, the natural log of 4 times the 7th root of 11. I should have been putting squigglies for these since we're using decimal approximation, so these are approximately. And our last one is about 1.729 if you throw that into your calculator. Example 6 says, find the domain of the function f of x equals log base 2 of x squared minus 25. Now, we've mentioned this previously, but you might have forgotten. When we're taking a logarithm, we can only take the logarithm of a positive number, regardless of what the base is. So here we happen to have log base 2, but that doesn't matter. When you're entering in a logarithm or you're calculating a logarithm, you can only take the logarithm of positive numbers, which means in this case that our argument inside of the logarithm, in this case is x squared minus 25, we need this to be positive or greater than 0. So previously we've learned how to solve nonlinear inequalities, and more specifically this is an example of a polynomial inequality, or more specifically a quadratic inequality. Now x squared minus 25 is a difference of squares, so I can factor that into x minus 5 times x plus 5. We want to know when this is greater than 0. So I'm going to rely on thinking about what the graph of this function looks like. I know that my vertex is going to be at the point 0, negative 25, which also happens to be our y-intercept. And then our x-intercepts are going to be at negative 5, 0 and positive 5, 0. So our quadratic, or our parabola, when we graph it, is going to look something like this. And I need to figure out when is this graph above the x-axis, and that's happening here. Everywhere before negative 5 and everywhere after positive 5 is where our y values, or our output values, are positive. So finally we can put all of this information together to tell us that the domain of this function is going to be from negative infinity to negative 5, and then we have to make sure that we're not including negative 5, union, and then parentheses 5, infinity parentheses. So here is our final answer for our domain, so that we end up with a positive number inside of the parentheses of our logarithm. It turns out that some scientific calculators don't have a way to compute a logarithm with any base and will only compute common or natural logarithms, but there's a way around this. So this is called the change of base formula for logarithms, and it says, let a and b be any real numbers, then log base b of x is equal to log base a of x divided by log base a of b. So it turns out that you can use this formula to get around if you have a calculator that does not allow you to alter the base of a logarithm, and say your calculator only has the common logarithm or the natural logarithm. This is how you would get around that. You would use the change of base formula. So let me just give you a quick example. We made a calculation earlier where we said log base 2 of 16 was equal to 4. But let's say that we wanted to throw this into our calculator and we didn't know what this was equal to. Based off this change of base formula, we could actually get this same number by computing the common logarithm of 16 and dividing that by the common logarithm of 2. And it turns out that it doesn't really matter what base you use. I could actually even use the natural logarithm as well. So I could take ln of 16 and divide it by ln of 2, and that would also give us the same answer, which should end up being 4. So go ahead and try that on your calculator, whichever kind you have, and see that these are all equal to 4. Let's move on to talking about graphs of logarithmic functions. Here are some properties of the logarithmic function f of x equals log base b of x. The first property says f of 1 is equal to 0 for all b values. If 0 is less than b, which is less than 1, then we have that the function is decreasing. If our b value, our base for our logarithm, is greater than 1, then our function is increasing. So we can see the two different scenarios here on our graph. First off, both of these graphs, they go through the ordered pair 1, 0. And again, if our base of our logarithm is greater than 1, then our function's increasing. And if our base is between 0 and 1, then our function is decreasing. And this is very similar to exponential functions. And then part 4, or property 4, says f of x is 1 to 1 for all values of b. Since b to the power of x and log base b of x are inverse functions, the graph of log base b of x can be obtained by reflecting the graph of b of x in the line y equals x. Example 7 says sketch a graph of the functions f of x equals log of x and g of x equals the natural log of x. Let's start off with f. So if I don't know what the graph of a function looks like, sometimes making a table is helpful. If I were to plug in 0, then that's actually going to end up being undefined. And you can see that if you were to plug that into your calculator. And we said earlier that we can only plug in positive numbers into our logarithms. So if I plug in 1, my output is going to be 0. I'm going to plot a point there. And then the next input value that's going to give me an integer output value would be 10. So the output value for 10 would be 1 because log of 10 is 1. So I'm going to go ahead and count 10. So we've plotted that point. Now I also want to plug in another input value that would give me an integer output value, and that's going to be 1/10. Log of 1/10 is equal to -1. So that's going to be about here. And our function is going to grow very slowly because, remember, this is the inverse function of y equals 10 to the power of x, which grows very quickly. So it's going to look something like this. And it turns out that there is a vertical asymptote at the y-axis. So x equals 0 is a vertical asymptote of this function. And our graph's going to look something like that, but not quite as crooked. All right, so I've gone ahead and I've graphed g of x by using a table. I wanted to try to make this one a little bit less crooked than our previous graph. So notice that this one is increasing faster than the previous one is. So it ends up looking something like this. And that concludes this video.